All right, good afternoon, everybody. Screen share has finally gotten its life together so we can get started. There's no due now, but if anybody had any pressing questions from last week, or if you have any questions about kind of logistics, where the class is going, that sort of thing, this would be a good time to ask. If you don't have any questions, then let me know if you're ready to just jump on into it. Go for it. What's your question? Okay, if you send me a message through course messages, I can look at it, and I can look at Mastering Chemistry to see what answers you've entered, so I can give you some insight on that. All right, then let's get into it. We're finishing up Chapter 8, and then we're going to go back and do some exam review that'll refresh you on what we did last week from Chapter 8, along with Chapter 7. The next couple of topics, while it's still in the same chapter, it almost seems like it's from a different chapter. So we're going to be talking about moles eventually, but it doesn't connect as well with what we did last week, and that's why I broke it up. We're going to start with talking about the percent composition. All that means is you list the mass percent of each element. So if I had methanol, CH3OH, the percent composition would tell me what percent of this compound is carbon, what percent is hydrogen, and what percent is oxygen. What we need to figure this out is two things. The first thing is the molar mass of methanol. As a refresher, take a minute and calculate the molar mass for methanol. If you don't remember how to do that, that's okay. But dig through your notes and you can put your answer in the chat. Yep, that's about what I got. So I'll write out how we got there. You're going to take the carbon plus 4 times the hydrogen plus the oxygen, which you can put that as 16 or you can put it as 15.999. You're going to get ballpark the same answer. So that's our molar mass. The percent composition takes the number of grams in 1 mole of each element over the molar mass of the compound and multiplies by 100%. And that gives you the percentage for each element. For carbon, and I should mention that you multiply by the number of moles or the subscript that you see. Carbon, there's only one carbon. So we're going to put 12.01 grams here. over the molar mass of the whole compound. And multiply by 100%. For hydrogen, there are 4 hydrogens. Go ahead. What's your question? Mm-hmm. So it's the number of each element that you have. So carbon, we got 1. Hydrogen, there's 4 of them. So we're going to do 4 times the molar mass of hydrogen. You're welcome. So if you do that math, it's 12.58%. I want you to try to fill in what the percent oxygen is going to be using the same method. When you get an answer, let me know. That's percent composition. When you add them all up, you should get 100%. It might be like 100.3 or 100.5 or something like that. That's fine. With rounding, that happens. But it shouldn't be 110%, okay? Now I want you to try it yourself. Calculate the percent composition of aspirin. That means that I want you to tell me the percent of carbon, percent hydrogen, and the percent oxygen. Oh, sure, I can go back. So do the same thing that we just did for methanol for the percent composition of aspirin. I'll give you a couple of minutes, and then I'll check in. I'm going to start writing some things out. We need the molar mass of aspirin before we can do anything with the percentages. Your molar mass should be somewhere in the ballpark of about 180 grams per mole. From there, for the percent composition, we've got 9 carbons times the molar mass divided by the molar mass of the compound. So that last digit, it depends on the periodic table that you use. For the exam, you'll all use the same periodic table. Some periodic tables have 2 decimal places, some have 3, some round differently. So that kind of contributes to the differences in the molar mass. And that's why I'm not too big of a stickler on it when it comes to your homework. Mastering chemistry, however, you should use the one that comes with the book for the best results. So for carbon, you should get somewhere in the ballpark of 60%. There are 8 hydrogens. Excuse me. There are 8 hydrogens. We do the same thing. And you should get somewhere in the ballpark of 4.5%. And I'm rounding a little bit here. So your answer should be somewhere near there. And for the oxygen, if you use 16 times 4, you should get around 36%. So that's the percent composition. Do we have questions on that? Okay. Hold on to that concept in the back of your head, because we're going to build just like we did before. Seems like we're going to talk about a slightly disjointed topic, but we aren't. We're going to join them together in just a minute. We've been talking a lot about number of moles, doing calculations on amounts of moles and stuff like that, mass. But we haven't really looked at the compound itself. We're going to talk about empirical formulas for a second, do some calculations, and then we're going to talk about molecular formulas. The empirical formula of a compound is just the simplest whole number ratio of ions in a formula unit or atoms in a molecule. Is there ever going to be a specific way we have to round the numbers? So when it comes to molar mass on an exam, I will tell you how many significant figures I want. And when it comes to doing problems where you need to use a molar mass or something like that, the difference in sig figs and your molar mass is not going to affect your answer enough. So if you're using the sig fig rules that we talked about, where if you're doing multiple calculations and you look at the given information, if the given information has 3 sig figs, you report 3 sig figs. You're welcome. So back to empirical formulas. The empirical formula is just the whole number ratio, the simplest whole number ratio that you can get for a group of elements or ions. If we have benzene, its molecular formula, so what it actually is C6H6. If we reduce that down as much as possible, the ratio is 1 to 1. C6H6, that's the same thing as saying 1 carbon for every 1 hydrogen. So that empirical formula is CH. If we have a molecular formula for octane, that's C8H18. So there are 8 carbons and 18 hydrogens. We can reduce that down and say 4 to 9. That is the simplest that you can go and still be similar to octane. This seems a little bit abstract, but it will make a little more sense once we do a problem. So if you don't mind, I'm going to go ahead and show you a problem and put it in context. Sure, I can repeat that. So the empirical formula is the simplest whole number ratio of atoms or ions in a formula unit or a molecule. If we look at octane, its molecular formula, so what it is in real life, is C8H18. The empirical formula, we're going to reduce those subscripts down as far as we can to get the simplest whole number ratio. Both of these numbers you can divide by 2 and get 4 to 9. That is as simple as you can go. So that is the empirical formula. You can make compounds that are multiples of this empirical formula. But like I said, it'll make a little bit more sense when we put it in the context of a problem. So let me go forward and show you a problem, and then we can address the questions that we have after that. The reason we care about empirical formulas is because given some information, we can actually calculate what the empirical formula is for a compound. Let's say that you have a sample of chromium and you heat it with excess sulfur and you make a certain mass of chromium sulfide, but you don't know what the empirical formula is. You don't know how many chromium atoms you have versus sulfide. What is the empirical formula? Looks like something that we can't solve, but it is. Let's break down what we have. We know that we're starting with a certain amount of chromium. We heated that with sulfur, excess sulfur, and we made some kind of compound that has chromium and sulfur. We don't know what the subscripts are, so that's why I put X and Y. If we know the number of grams of each reactant, then we can figure out the number of moles of each reactant. So once we calculate the grams, we calculate the moles. We can simply subtract to figure out how much sulfur was added to this chromium to make our product. When you do that subtraction, you get 0.716 grams. So all we're doing is figuring out how much sulfur reacted with the chromium. Are we okay so far? Now we can take those masses and convert to moles. Now we gotta know. Okay. Do you have a specific question? Or do you just need to be repeated? Okay. We know that we're starting with a certain amount of chromium. We know that our product, we made a certain amount. What we don't know is how much sulfur was added to make that product. So if we subtract the amount of product we have, we take that and subtract the amount of chromium, then that should give us the amount of sulfur in grams that was combined with the chromium to make this new compound. And that's all we've done so far. Is that better? The next step, I subtracted. So 1.878 grams minus 1.162 grams. All I did was subtract. Now we have enough information to calculate the number of moles. So this was step 1. Step 2, we're going to take those grams and convert to moles. Remember that when you just have an element like chromium, you're just going to look at the periodic table and see what it says and write that number in grams. We'll do the same thing for the sulfur. So now we know how many moles of each element is in this compound. The third step is to find the ratio. What that means is we're going to take the number of moles that we have and divide them. Looks like a 0 got left off here. There should be 0.0223 for each of them. If we divide these two, we're going to get 1. But that doesn't really help us. What that 1 really means is that you have 1 mole of chromium for every 1 mole of sulfur. And this tells you what your empirical formula is. Because these numbers here are the subscripts. So it might take a second for you to wrap your brain around that. I have another example for us to work through. But these are the steps for figuring out an empirical formula if you're given the masses of different samples. So talk to me. Is there a certain place that you got lost? Does it make sense? Do you need something to be repeated? It will not always equal 1. That's why writing it out like this is much more helpful. We'll do an example where it doesn't equal 1. Let me know if you just want to walk through another example, and I can ask you some questions along the way, and then we'll see if you really get it. I think that might be the best way to do it. So let me know if you're ready for that. Yeah. Let's walk through the next one. So it's the same type of problem, only instead of chromium, we've got cobalt. We've got 1.115, grams of cobalt. We're reacting it with excess sulfur. And we're making 2.025 grams of this cobalt sulfide, but we don't know what the empirical formula is. Whenever you're given the two masses like this, the first thing you're going to do is figure out how much of your reactants you have. We know one reactant and one product, so we can subtract to figure out how much sulfur. Do that subtraction and tell me what you get. So now we know how much we have of the cobalt and how much sulfur. The next step is to convert our grams to moles, and that always uses the molar mass. I want you to convert the cobalt and the sulfur to to moles. And let me know what you get. I want you to convert the grams of cobalt to moles and the grams of sulfur to moles. I'll start filling it in here. So you should get more moles of sulfur than you do cobalt when you finally finish that conversion from grams to moles. So when we do our division to find the mole ratio, it's not going to be 1-to-1. When you don't have equal numbers of moles, you want to take the largest one and divide by the smallest one. We've only got 2 here, so that's what we're doing. If you have more than 2, you would take each of the numbers and divide by the smallest number of moles. And we'll do one where you've got more than 2 elements in a compound. But we're keeping it simple for right now. So if I take the number of moles of sulfur and divide by the number of moles of chromium, what I end up getting with my calculator is 1.5. That doesn't help. You have to remember what 1.5 can be written as. What it really means is 1.5 moles of sulfur for every 1 mole of chromium. Remember, every whole number can be written over 1. So you can make it into a fraction. But again, for an empirical formula, you need a whole number ratio. To make the top number a whole number, we have to multiply by 2. So what you get is 3 moles of sulfur for every 2 moles of chromium. The 3 and the 2 are the subscripts for the empirical compound. Oh, I'm writing chromium because that's what we did before. It's cobalt, y'all. They're so similar. Thank you for that. You multiply it by the number that will give you a whole number at the end. Usually the magical number is 2. So with our cobalt sulfide, the empirical formula is CO2S3. So how do we feel about that? Questions? You'll definitely have some of these on your mastering chemistry. So I wanted to give you an idea of how to do it. Sure, I can repeat the ratio part. So that's the most important part. Because I'm sure getting the moles, not a problem. But figuring out the mole ratio and what it means is the hardest part. You're going to take the smallest number of moles, and that's what you're going to put in the bottom of your mole ratio. Then you take every other number of moles and you do the division. We've only got two elements here. So you take the sulfur and divide by the number of moles of cobalt. When you put that into your calculator, it's going to tell you 1.5, which doesn't help you. You need to rewrite that in terms of the moles of sulfur and the moles of cobalt. So 1.5 is like saying 1.5 moles of sulfur for every 1 mole of cobalt. It's just a little math trick. Since 1.5 is not a whole number, you have to multiply by a factor to make that 1.5 into a whole number. If you multiply by 2, then you get 3, which is a whole number. So 3 moles of sulfur for every 2 moles of cobalt. Whatever these numbers are in your mole ratio, that's what your subscripts are in your empirical formula. Does that help? Any other questions? Let me know if you're ready to move on. So you want the smallest whole number ratio. Whatever factor that you can multiply by to get that is what you multiply by. So if it was 1.3, you'd multiply by 3. Does that make sense? It's practice. As long as you understand the idea of getting that ratio and you can get to the 1.5 part, then trial and error, you can figure out the subscripts. That's fine too. Yeah, as long as you end up with the simplest whole number ratio, I don't care what you multiply by initially. If you multiply by 6 or by 10 so that you can see it better, and then you reduce it down, that's fine. You're welcome. Okay. There's another way that we can do empirical formulas. Instead of getting the number of grams of a product in a reactant, we can be told the mass percent or the percent composition of a compound, and then asked, what is the empirical formula? Looks like we don't have enough information, but we do. Percentages have to add up to 100%. If we assume that we have 100 grams of our compound, then that would mean that instead of 92.2% carbon, we would have 92.2 grams of carbon and 7.83 grams of hydrogen in our compound. This is the only way that we can figure this problem out. Once you make that assumption and you have your grams of each element, it's literally the same process. We take the grams and convert to moles, we figure out the mole ratio, and then we put together our empirical formula. You can put those in your calculator and let me know what you get for the number of moles of each. We've got our carbon. And that's moles. We're switching from grams to moles. So 7.68 and 7.77, if we do that division, we're pretty much going to get 1. So that means 1 mole of hydrogen for every 1 mole of carbon. Our empirical formula is CH. Again, the only difference here is we started with the percent composition, and we assumed that we had 100 grams of our compound, so we can write grams instead of percent for each element. I have an example for y'all to do. So do you want to move on and do the example, or do you have questions on this? We're going to get there, just not yet. So we've got a percent composition of bismuth oxide, and you have to figure out the empirical formula. I will give you 5 minutes. If you get stuck, that's okay. When I check in with you in 5 minutes, let me know that you got stuck. If you got an answer, that's great. But the goal here is to see where you get stuck. Sure, Talia, I can go back for a second. And once I go forward, we'll start the timer. All right. So we'll start the clock now. 5 minutes. See how far you can get. And then I'll solve it. I'm going to start setting up the problem. If you haven't finished yet, that's fine. Keep on working. That's what I got to at the end. I'll go over it for everybody, though. I don't want you to be sitting there waiting. So the first step is always to convert your grams to moles. And that's what we did for the bismuth and for the oxygen. Now we need to do that mole ratio. There's only 2 elements here. So we'll put the biggest one on top. That's the oxygen. And we'll divide by the smaller one. That's the bismuth. Your calculator is going to tell you 1.5, which isn't exactly helpful. You need to translate that into 1.5 moles of oxygen for every 1 mole of bismuth. And to write that as a whole number ratio, you can multiply by 2. Those numbers are going to be your subscripts. The metal always goes first. That's your empirical formula. So I know a few of you got it right. The rest of you, if you got stuck, let me know. If you think you just needed more time, let me know that too. I want to see how we're doing. Yeah, that's totally understandable if you needed more time, because we're just starting this, so 5 minutes isn't a lot of time. But the goal is for you to feel comfortable with saying, I think I could have got to that if I had enough time. So let me know if you're ready to move on or if we need to go over this again. Then let's move on. Here's one, like I promised, where you have more than just 2 elements. In this case, you have 4 elements. You're going to do the same thing, but when it comes to the mole ratio, you're going to need a ratio. You're going to take all of the moles and divide by the smallest number of moles. So just give it a shot. I'll give you another 5 minutes for this one, and then I'll jump in and start solving it and help you out if you get stuck. If you get an answer, toss it in the chat. So 5 minutes to get started, and I'll check in. I'm going to start solving the problem. Yes, sir. Right. Mm-hmm. So you're going to take... So which one is the smallest out of those? The smallest one should be the oxygen. So you're going to take all the other ones and divide by oxygen. So let me write out what I got for the moles, and then I'll move on to doing the mole ratios for each one. Yeah, you can go ahead with your question while I'm still writing. It's going to take me a minute. No, 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 no. We are not adding anything. We're dividing by the smallest. Yeah, so you take all of the other ones and divide by the smallest. I'll show you exactly what I mean. Yeah, if there's another question, go right ahead. My handwriting's I'm a little bit slower because I'm still working with a bum pinky. I injured my pinky in a really weird way. Stuff like that usually happens quick, and you're like, what in the world? So, bear with me. So, you should have gotten these numbers ballpark. The carbon, hydrogen, and nitrogen are about the same number of moles, but the oxygen is the smallest. Yeah, I just saw that screen sharing is reconnecting. So we're going to wait. It took a long time for screen sharing to connect for class earlier. So I can talk through what it is, and I'm going to keep writing, and hopefully it'll just catch up so that you can see it, because it's going to take me a minute to write it anyway. We said that the smallest one was the number of moles of oxygen. So you're going to take your moles of carbon and divide by the number of moles of oxygen. And that will tell you how many moles of carbon you have for every 1 mole of oxygen. Your calculator is going to tell you 2.5, and you have to translate that to 2.5 moles of carbon for every 1 mole of oxygen. But that's not a whole number. So what that really means is 5 moles. Hey, look at that. 5 moles of carbon for every 2 moles of oxygen. It shouldn't be 2.8. Did anybody else get 2.8 instead of So are you saying when you divided the number of moles of carbon by the number of moles of oxygen, you got 2.8? Okay, are we talking about the number of moles of carbon? We gotta give some units here. Okay. So if we're talking about the moles of carbon, 2.991 versus 2.992, you're going to get the same answer. 2.8, you'll get approximately the same answer as well. The second part, you should not get. Nope. I get 2.499 and change. I just quickly redid it again just to make sure. Alright. You're scaring me, Finelli. Don't scare me like that. You know this is my afternoon class. I'm already crazy. Yes, go ahead. We have to do all of them. It's the same number, so you're going to end up with the same mole ratio. So right now, we've got carbon, hydrogen, nitrogen, and oxygen. And we're comparing all of those, the carbon, hydrogen, and nitrogen, to the oxygen. We can fill in the 5, and we can fill in the 2. The hydrogen and the nitrogen are going to give you the same ratio. You can do it all out. And you'll get the same thing. So when you've got more than 2 elements, you use the smallest one and divide all the bigger ones by that. That will give you your ratio. Are there any questions? Or do you just need some practice? No. No. But you'll always get, so maybe the ratio would be 2 to 1 for carbon and then 3 to 1 for hydrogen. Then you'd have C2H3O. So whatever you get for those mole ratios, that's what your subscripts are going to be. Other questions? Yes. So you have to multiply by 2 to go from 2.5 to 5. And you have to multiply the top and the bottom. And then I just left the oxygen at 2. Okay? Patrick, you had a question? So if you have the same number of moles like we do here for the hydrogen and nitrogen, you don't have to show the work to divide again because the numbers are so similar. But if they were different, you'd have to divide. So I don't have another example of this, and we have other topics to cover. So unfortunately, we're going to have to move on from the empirical formulas to do the molecular formulas. But we do have another example where we're going from figuring out the empirical formula and the molecular formula, and there's more than 2 elements. So Talia, if you can hold on, we'll get to an example that covers more than 2 elements again. We just need a few more slides between us and that. Is that fair? Okay. So that was the empirical formula. We're going to add another concept on, the molecular formula. The molecular formula is just a multiple of the empirical formula. We figured out the empirical formula for acetylene several slides back, and it was CH. If you're told the molar mass of your compound, then you can figure out the molecular formula. The first step is to calculate the molar mass, which I abbreviate MM, of your empirical formula. Our empirical formula is CH. It's a pretty easy one to do. It's about 13. The next thing you do is calculate the N. And that just tells you the multiple of your empirical formula. That N is what we're going to multiply by to get the molecular formula. Now, how do you calculate N? You take the molar mass of the molecular formula and you divide it by the molar mass of the empirical formula. So for our acetylene example, our N would equal 26 grams per mole divided by what we calculated for the empirical formula. And that's going to give you about 2. What that means is we're going to multiply our empirical formula by 2. So that is our molecular formula. Questions? I have an example for you to try. So you have the empirical formula of lysine, and you have the molar mass. Oh, sorry, Finelli. Ladies, let me know when you're ready to. So I want you to try this one on your own. You have the empirical formula for lysine and the approximate molar mass. Figure out the molecular formula. I give you 2 minutes to do this. And if you don't finish, that's okay. But as long as you understand the process, we're good. I'm going to start writing some stuff out here. So you first have to figure out the molar mass of the empirical formula. You should get something in the ballpark of 73 grams per mole. I got 73.093. But depending on which periodic table you use, these last couple of digits might fluctuate a little bit. But you should get somewhere in the ballpark of 73. To calculate N, you just take the molar mass of lysine and divide by the molar mass of the empirical formula. That gives you 2. When you multiply everything by 2, it's just like in math. That's the empirical formula, or excuse me, the molecular formula that you should get for lysine. Go ahead. So you have to calculate the molar mass. So that's 3 times the grams per mole for carbon plus 7 times, yeah. I just didn't write all that out. Okay. Other questions? Okay. Then we're going to keep pressing forward. Now we're going to put it all together. I told you to keep percent composition in the back of your head. We worked with it a little bit with empirical formulas, and now it's showing up again. What we're going to do here, and I did this example in the YouTube video, but I'm going to do it again so you have the opportunity to ask questions along the way, and then you'll get to do one yourself. We're going to take the percent composition of a compound and the molar mass and figure out the molecular formula. The only way you can do that is by figuring out the empirical formula first. Just like before, when you have percent composition, you assume that you have 100 grams of your compound. That way, you can take those percentages and make them into grams. That will help you a lot more than percent. So if we have all of these numbers for our moles, what's our empirical formula? That's the mole ratio for all of them. It's 1. So if you were to write out the empirical formula, what would it be? Exactly. We'd have 1 of each thing. That's the first part. Now we need to do what we just did, like with the lysine. Calculate the molar mass of the empirical formula. You're going to take the mass of carbon plus the mass of hydrogen plus the mass of chlorine and add all those together. When you do that, you should get something around 48.5, give or take. Once we figured out the molar mass of the empirical formula, what was the next step in figuring out the molecular formula? We have to find N. We take the molar mass that we're given in the problem for the compound, and that's 290 grams per mole. We divide that by the molar mass of the empirical formula. When you put that into your calculator, you get 5.98. That's 6, okay? It may not come out exactly to 6.0 or 2.0 when you do it, but it should be close enough to where if somebody gave you $5.98 instead of $6, you'd be like, it's 2 pennies. It's not a big deal, right? So when we have our N, that's the kind of calculation we're doing here. The final thing is to write out what our molecular formula is. So we're taking our empirical formula and multiplying it by 6. Questions about that? I have one for you to try. So if you're ready to try one, let me know that too. What about the empirical formula, Finelli? Yeah, they're all about the same number of moles. They're all about 2 moles. So that means that the ratio is 1 to 1 to 1. Alrighty. So now I want you guys to try this one. And like I promised Talia, there's 3 elements here. So you'll get to practice with that too. You're trying to figure out the molecular formula for lactic acid. You've got the approximate molar mass, and you've got the percent composition. I'll give you 5 minutes to get started. Then I'll start writing because I'm a little bit slow. and we'll see how you do. Take 5 minutes, and if you get stuck, let me know. I'll get started writing here because it's going to take me a minute. Please keep working, and if you have a question, just hop on in. So hopefully everyone was able to get to the number of moles. And Patrick asked the question about how we get to that empirical formula, so I'm going to go over that again. The moles for carbon and oxygen are the same, 3.33. So you can use either one to figure out that empirical formula. We're going to take the moles of hydrogen and divide by the number of moles of carbon. I just chose carbon because it's at the top. You could do the same thing with the oxygen because they're both the same number of moles. Your calculator is going to tell you 2. You need to translate that to 2 moles of hydrogen for every 1 mole of carbon. Because the oxygen is the same, it's also going to be 2 moles of hydrogen for every 1 mole of oxygen. Your empirical formula is CH2O. From there, we need to calculate the molar mass of that empirical formula. So you take the carbon plus the 2 hydrogens plus the oxygen. Tell me what your what the molecular formula is, not just the N, but the question's asking for the molecular formula. So your molar mass should be about 30. Your N is 3. So when you multiply, you're going to multiply by 3. And yes, that is your molecular formula. You will absolutely see a question like this on the exam. So you need to be able to go from percent composition to the empirical formula to the molecular formula. Talk to me about how this went for you. You have questions? Did you get stuck? Or do you just need to practice? So the homework will help you practice, for sure. And if you still have questions, you can come to me in office hours tomorrow. So for those of you who aren't speaking up or asking questions, you don't have to, just sit on it. You can always come to me. So we're going to take a short break here. Well, I'll give you the option, all right? After this, it's exam review. So whatever exam review we get done this week, we'll have time to do some next week and finish up exam review. If you want a break, we can take a 10-minute break and then just get through a couple of questions this week. But we have to get through what we need to get through for Chapter 9 next week. So it's kind of like, how much exam review do you want versus how much do you want a break? So let me know. If you want a break, you can raise your hand. And I won't count it against you. We can take a short break then. How about 5 minutes so you can run and get something to drink or whatever. If you would like to go for 5 minutes, you're free to. I will just keep going. If you want to take 5 minutes, we're finished with Chapter 8 material. You're an adult. You can go for 5 minutes. If people want review, I'll give you review. But if you feel like you need a minute, catch your breath and jump back in. That's totally fine. So we'll get right into the exam review. You have an exam next week. It's on chapters 7 and 8. We just finished up all the material for 8. So this review is going to focus on chapter 7 and what we did last week for chapter 8. Take a couple of minutes and answer this question. How many molecules of hydrogen gas are in 22.4 liters of hydrogen gas at STP? Feel free to put your answer in the chat when you get it. I'm going to get started setting up the problem. We're asked about how many molecules, and we're given a volume. So the problem type is volume to molecules. We can't jump directly there. You have to look at moles first. So that's the connector. Starting with 22.4 liters, we need to write a conversion factor that's going to get us from liters to moles. The only thing that relates volume to moles is molar volume. We'll put the moles in the top and liters in the bottom. For the second part, we're going from moles to molecules. We use Avogadro's number for that. Whoops. We'll put molecules in the top. That's what we want to end up with. Moles we'll put in the bottom so they cancel out. So if you knew the definition of molar volume and the relationship of 1 mole to Avogadro's number, you didn't have to do all that math. But if you didn't remember, you can still set it up. So how do we do on this one? Yeah, with chapter 8, there's a lot of remembering, okay, it's this problem type or that problem type. So review and doing problems is the best thing that you can do. And doing the chapter 8 Mastering Chemistry will help you do that too. You're welcome. Now we're going to jump into, this is a chapter 7 question, reviewing what a chemical change is. So just as a reminder, a chemical change, what we're talking about is a chemical reaction. And there's the 4 different things that you can observe that lead you to the conclusion that you're observing a chemical change. What I want to know is, from A, B, C, and D, which of these are chemical changes? It could be all of them, it could be 2 of them, it could be 1 of them. Let me know in the chat. We have a vote for all of them being chemical changes. 2 votes. All right. So we got some answers kind of all over the place. We'll go through one by one. An Alka-Seltzer tablet fizzes in water. Yes, that is a chemical change. The fizzing, bubbling, that's making a gas, and that's evidence of a chemical change. Letter B, we're heating iron and air and producing a dark red solid. That's absolutely a chemical change. We've got a change in color, and if we're heating iron and air, that's combining 2 things and adding heat. So that's definitely a reaction. C, we have a spilled solution dries on the lab bench, leaving a white residue. That one is not a chemical change. That's just evaporation. So a change of state, that's a physical change. We're going from something dissolved in water to something not dissolved in water. Letter D, you're mixing 2 clear aqueous solutions and you produce a blue color. That's absolutely a chemical change. Whenever you see a color change like that, it's an indication that a reaction has occurred. So the answer here should be A, B, and D. We good on that one? Go ahead. Mm-hmm. Not just the heat, but the way that it's worded. So you're heating iron in air. Remember that air is a bunch of gases. So air is a chemical. So you're heating two compounds together and you're producing a dark red solid. That's describing a chemical reaction. You're taking two things and combining them to make something new. And that something new is red. So there's a color change too. Other questions? Then let's keep going. Classify and balance the following equation. Word to the wise here. The Chapter 6 check-ins. I know a lot of you know the material better, but you have to read the instructions. So if you did not classify and you just wrote the name or the formula or you just wrote the classification, that's only half of the question. So you can only get half of the credit. For the exam, make sure that you read because you may have to classify and balance. Make sure that you do both. So tell me what type of reaction it is and then balance the equation. And I'll give you a couple of minutes to do that. If you get your answer, you can just write out your coefficients from in order from reactants to products and put that in the chat. But I'll give you a couple of minutes to get started. Even if you haven't finished balancing the equation, let me know what type of reaction this is if you figured that out. So this is definitely a double replacement. Finelli, look at your coefficients. You can simplify those. You always want your coefficients to be the lowest common denominators. It should be as simplified as possible. I'm going to go through it and show you how to balance it here. Remember, with balancing equations, you want the same number of atoms or ions, because we have some polyatomic ions here, on each side. We start off by making our chart to figure out how many of each atom we have on the reactant side and the product side. So we're clearly not balanced. I always like to start with the polyatomic ions. You look for the lowest common denominator between the number of ions on the reactant side and the product side, and that's 2. So we're going to multiply where we see the nitrate ion by 2. Always put that number out in front. Now we need to see what we did, because putting that 2 out in front changed more than just the nitrate. We haven't touched anything on the reactant side, so we can just copy that over. On the product side, the mercury is the same, so is the bromine, but we've changed both the sodium and the nitrates. The nitrates are balanced, but now the sodium is unbalanced. So let's deal with that. Again, the lowest common denominator is 2. But this time we're going to multiply by 2 on the reactant side, and that will even things up. But again, that affects more than just the sodium. And if you feel comfortable to do this without writing a table every time, go for it. But if you do need the table, that's perfectly fine too. And it'll help you kind of catch your mistakes. It's easy to make simple math errors when you're doing this. So on the reactant side, we've still got the same number of mercuries and nitrates, but we've now got 2 each of sodium and bromine. The product side, we haven't changed at all. Now we're balanced. So the coefficient should be 1, 2, 1, 2. I know we haven't talked about Chapter 7 in a little bit, but how'd we do on that one? All right. That's why we're doing exam review. Brush off the cobwebs. Oops. All right. Definitely want to get to this one. Calculate the mass of a single molecule of carbon dioxide. And you need me to go back? Sure, I can go back for a second. All right. So I definitely want you guys to do this one. You will absolutely have a question like this on your exam. So look back through your notes if you need to and figure out how to do this problem. I'll give you 2 minutes to get started, and then I'll start writing it out. Here we go. I'm going to start writing it out. We need to calculate the mass of a single molecule of carbon dioxide. That makes this a molecules to mass problem. For all of these, you have to go through moles. The first part, we use Avogadro's number. And that'll get us from molecules to moles. To go from moles to mass, you need molar mass, which I abbreviate MM. Let's calculate that molar mass real quick. So you've got carbon plus 2 oxygens. So you should get something like that. That's the molar mass. Now we need to set up our equation. A single molecule means that we have one molecule of CO2. One very lonely molecule. We're going to convert that to moles using Avogadro's number. The second part is taking those moles and using your molar mass to figure out how many grams. Since we're talking about a single molecule, it should be really, really small. We make sure that our units line up, and they do. You put it into your calculator, and you should get 7.31 times 10 to the minus 23 grams. So you had the right coefficient, but you needed that exponent. You're going to have a question like this on your exam. We went through a couple of them last week. So make sure that when you're studying for the exam, that you do a question like this. You'll see something like this on the exam review packet as well. So how do we do with this one? This is usually one of the trick questions that shouldn't be a trick question, because I tell you about it. But every year, it seems to trip people up. All right. We'll do this last one, and then we'll save the rest of the questions for next week. How many atoms are in 5.78 grams of iron? I'll start writing out how to solve this problem. We're given a mass of iron and asked about how many atoms. We can't go directly there. We've got to go to moles first. To go from mass to moles, you need the molar mass of iron. From moles to atoms, it's Avogadro's number. Starting with our mass of iron. For this, you just have to look at the periodic table. You don't have to do any calculations for the molar mass. Just report what's on the periodic table in grams. There you go. For the next unit factor, you've got to use Avogadro's number. We want to get rid of moles and end up with atoms. So the moles go in the bottom, and the number of atoms goes in the top. Yep, that's what you should get. 6.23 times 10 to the 22nd atoms. Don't forget your units. How do we do on that one? Alright. So I don't think we have quite enough time to do this question. There's a couple more, I think. We'll pick up with this. This is a solubility question next week. Oh, sure, I can go back. So we'll pick up with more exam review next week. We'll do a few more questions before we dive into Chapter 9. You're very welcome. So we had a couple more questions to go. We don't have quite time for that. I want to give you your reminders. So Chapter 8 for Mastering Chemistry is due on Sunday. There's no check-in this week. I just want you to get that Mastering Chemistry done. Your exam is next week. It's going to cover Chapters 7 and 8. So everything that we did this week, last week, and the week before. It'll be available on October 28th. It will close on the 30th. You will need to show your work for this one because there's a lot of math. If you have any questions, go for it. Otherwise, you're free to go.